Hi all. So welcome back to discussion on quantum theory of scattering. Today we'll have a last session on the study of the scattering of spinless particle. Okay, so we can just revise what we have studied about the study of scattering. So this is the a schematic representation of scattering study. So we'll have some incident particle which is described by symbol JIN, which is called the incident flux. Okay, incident flux means the number of particles crossing unit area in unit time. Okay, and we have a scattering center, and what we are interested is how many particles will be scattered through some solid angle d omega. And here we can define one important quantity called differential scattering cross section. So differential scattering cross section denoted by symbol d sigma by d omega is a function of theta phi, and it's defined as 1 by Jin dn scattering by d omega. Okay, dn scattering by d omega is the number of scattered particle per unit time per the solid angle d omega at an angle theta phi. Okay, so this is what is called the differential scattering cross section. And if you recall the total wave function, okay, so for such system, the total wave function of the particle can have two parts. One is the wave function of the incident particle plus the wave function of the scattered particle. The wave function of the incident particle will take very simple form because it represents a plane wave, and I can simply write which is a times e raised to ik dot r. And whereas the scattering part of the wave function would be spherical wave because it will be directed in all possible directions. There can be back scattering, forward scattering, and so on. So therefore, it can take the form e raised to I k dot r by r, and plus there will be some angular dependence, and angular dependence we can denote by symbol f of theta phi. This f of theta phi is called the scattering amplitude, and we have shown that this differential scattering cross section d sigma by d omega can take the form f of modulus of f of theta phi square in case of elastic scattering for spinless particle. Okay, so this is what we have discussed till now. Okay, and in the last class, what we have done is we have taken the Green's function formalism to find an approximate solution or approximate expression for the scattering wave function, and I will just write it down here. So the scattering wave function is possible to write the scattering wave function as minus mu divided by 2 pi h bar square integral e raised to ik modulus of r minus r prime all divided by modulus of r minus r prime v of r prime psi of r prime d cube r prime. Okay. Okay, so then what would be the total wave function? So the total wave function I can write as the incident wave function, which is sine of r, plus the scattering wave function. But a scattering wave function will just take the form minus mu by 2 pi h bar square integral e raised to ik modulus of r minus r prime divided by modulus of r minus r prime v of r prime psi of r prime d cube of r prime. Okay, now here no need to write psi total repeatedly, so better we can just delete this psi total. So this gives the total wave function. Now remember, this is not the solution for the scattering problem, because if you look at here on the right side, there is also psi, which is a function of r prime. So therefore, it is not a solution. It is just an integral equation for the wave function. Okay. Now we can have some certain simplification in this expression in asymptotic limit. So remember, this r represent uh, the position of the target, and whereas the r prime represent the position of sorry, this r represent um, r represent your not target. The r prime represent target, where r represent the detector. Okay, so then we can have some asymptotic solution for this expression. Okay, so we can have a schematic diagram. So we have a target and detector somewhere. So if this is your origin, then the position vector of target can be represented as r prime, and whereas the position vector of the detector can be represent position vector r. Okay, so we can have an asymptotic limit here. So asymptotic limit is when the target is very far away from the detector. It is r is much greater than r prime. If r is much greater than r prime, then it's called asymptotic limit. So in asymptotic limit, we can have a similar expression for this. Okay, so if r is much greater than r prime, then what about e raised to I k modulus of r minus r prime? Okay, so if r is much greater than r prime, what about modulus of r minus r prime? So modulus of r minus r prime is nothing but square root of r square plus r prime square minus 2 r dot r prime. So this is very simple vector addition. Okay, we can take r square commonly outside, so it will become r 1 plus r prime by r square minus 2 r dot r prime divided by r square is all raised to 1 by 2. So since r prime is much less than r, then we can say that this r prime by r square would be very small compared to the other two terms. Okay, so compared to the one and the second term, this r prime by r could be very small. Okay, then we can write modulus of r minus r prime as r is outside, then 1 minus 2 r dot r prime divided by r square all raised to 1 by 2. Because what I have done is I have neglected the second term compared to the first and the third term, because this would be, this is a quadratic expression. Okay, then here again r prime is much less than r, so therefore this quantity would be less than 1, and we can have a binomial expansion. So in case of binomial expansion, what we'll get is 1 minus, so this become 2 by 2, the 2 will cancel, it is 2 by 2 r dot r prime by r square, and we can neglect the higher order terms. So therefore this becomes r minus r dot r prime divided by r. Okay, or r minus unit vector r dot r prime. So modulus of r minus r prime can be written in this particular way. So therefore, your e raised to ik modulus of r minus r prime can be written as e raised to ik r minus unit vector r dot r prime. So this become e raised to ikr minus I k dot r prime, or we can write this e raised to ikr e raised to minus ik dot r prime. Okay, we can number this. Okay, best first we can number this expression. Okay, this can be some number equation number 10. Okay, better this is the part 4 of our lecture. So this expression can be written as some 4.1. And this can be written as 4.2. Okay. Now similarly, in the asymptotic limit, we can rewrite 1 by modulus of r minus r prime also. So 1 upon modulus of r minus r prime become 1 upon square root of r square plus r prime square minus 2 r dot r prime. So this become 1 upon r 1 plus r prime by r square minus 2 r dot by r prime by r square all raised to 1 by 2. So here we can have the same condition, that is r prime by r square would be negligible. Would be negligible in asymptotic limit, which is r much greater than r prime. So in the asymptotic limit, what we can write this expression as 1 upon r. This can be neglected, so this become 1 minus 2 r dot r prime all square all raised to minus 1 by 2. So this take the form 1 upon r 1 plus r dot r prime by r square. Okay, so now what we can do is we can take this 1 by r, we can take this 1 by r inside the bracket. So there will be two terms. The first term is 1 upon r, and the second term take the form r dot r prime by r cube. Okay, so if you look at this in the second term is proportional to 1 upon r square, but the first term is proportional to 1 upon r. And since r is much greater, so therefore we can usually uh, ignore the second term, and this can be approximated as 1 upon r. So in the asymptotic limit, 1 upon modulus of r minus r prime can be approximated as 1 upon r, and this can be equation 4.3. Okay, so we can substitute this 4.3 and 4.2 in our the previous expression 4.1. Okay, so better we can copy this. Okay, so this is our expression. Now we can have substitution. So in the asymptotic limit, the psi of r can be written as the incident wave function psi in of r minus mu upon 2 pi h bar square integral. So this can be written as e raised to ikr e raised to minus ik dot r prime divided by 1 upon modulus of r minus r prime can be simply written as r, and thereafter it become v of r prime psi of r prime d cube of r prime. So this become psi incident of r minus e raised to ikr divided by r mu upon 2 pi h bar square integral e raised to minus I k dot r prime v of r prime psi of r prime d cube r prime. Okay, so we have got a very good result. Okay, because if you compare this expression with the total wave function, this part, the part which is inside this curly bracket, take the form of a scattering amplitude f of theta phi. Okay, so therefore your f of theta phi is simply minus mu upon 2 pi h bar square integral e raised to minus psi k dot r prime v of r prime psi of r prime d cube r prime. Okay, so that's our the scattering amplitude. Now what would be the differential scattering cross section? The differential scattering cross section, by definition, it is we can denote it by symbol d sigma by t omega is function of theta phi. It is simply the mod square of the scattering amplitude for elastic scattering. Okay, and hence it takes the form mu square divided by 4 pi square h cut raised to 4 modulus of integral e raised to minus I k dot r prime v of r prime psi of r prime d cube r prime mod square. Okay, so that's all about the study of the scattering of spinless particle. So we have got a very compact expression for the differential scattering cross section, and we can keep that is in a inside a box, and is very important equation as far as we are concerned. Is very important equation. Okay, now this is important, but this is not a direct solution. We cannot find the differential scattering cross section directly from here until we know what is this psi. Okay, so we need to know the expression for the wave function to find the differential scattering cross section. So finding this psi of r prime is again a very basic question. So that is basically the solution of our differential equation, the wave function. Okay, but there are methods to find this wave function, the scattering wave function, the total wave function approximately. And we will use one of such approximation method is called the Bond approximation or Bond series. Okay, so in the next class, what we'll employ is we'll have a method called Bond series method, to find the wave function of the scattering wave function or the scattering particle approximately in a series method. Okay, so I think this is enough for us for the study of scattering of spinless particle, and you can um, patiently go through this lecture because there are very subtle points in between. So you can go through the lecture and as well as read your textbook in order to get a very good understanding of the quantum theory of scattering of spinless particle. Okay, so thank you all. So we'll come back with the discussion of bond series in the next class. So thank you.